Ik ben te verstaan voor de mensen die een koptelefoon op hebben. Ja, kijk, heel goed. Welkom dan voor de derde en laatste Smart Talk hier. We gaan weer twee onderzoekers aan het woord laten. Die presenteren hier kort hun onderzoek en daar praten we dan even over door. Denk ook alvast na over vragen die je hebt die opkomen tijdens de presentaties. Want het is wel leuk om die na afloop te stellen. Even kijken, we hebben twee onderzoekers die hun onderzoek gaan presenteren. In dit geval op het gebied van healthcare, gezondheidszorg. En de eerste spreker is onderzoeker en docent toegepaste natuurkunde en photonics. Dat is de wetenschap die zich bezighoudt met het licht. En zij zal een onderzoek presenteren dat gaat over sensors die gebaseerd zijn op nanotechnologie en die steeds vaker ingezet worden in de zorg om snel en goedkoop metingen te doen die vroeger in een laboratorium moesten plaatsvinden. Maar hoe maak je nou die sensoren die dat kunnen en hoe zorg je ervoor dat dat allemaal goed functioneert? Geef haar een warm applaus. Sarah Marit Rijn.
Dankjewel, Michiel. Hello. My name is Sarah Marit Rijn. I'm from the research group of Nanophysics Interfaces from Cas Damen. I want to tell you today about a research about photonics interfacing. Like Michiel said already, we are working with sensor-based systems, and one of the technologies we are using is based on photonics. One of the application areas can be found in point-of-care devices. Point-of-care devices are devices that are used at the point of the patient. So when a patient really needs the care, blood sample or a urine sample or a saliva can be taken from the patient and can be delivered to a system that is able to analyze the sample on the spot. It takes several minutes before the test results are known for the clinical expert, and the clinical expert can read out the test results and discuss this with his patients. This type of technology provides a very efficient way of providing care for people because you have immediate access to test results, which can speed up the diagnosis part, and also treatment of illnesses can start sooner. We have delivered two demonstrators recently in the Nanophysics Research Group, which are aiding in the development of such point-of-care devices. The top one is for a blood analysis, and the lower one is for acetone levels, which are secreted by the skin of a top spotter when he's working out. You can monitor the process when he is reaching a certain metabolistic state. Well, what it basically is a lot of readout electronics and some sample delivery system, and the heart of the machine, the sensor. So these two devices are comprised with a photonic sensor inside. So the photonic sensor is the heart of the machine, and it's a very small and thin device. There's a photonic integrated structure on top of it, where you can make all sorts of light guiding structures. Light is transferred via fiber into this structure, and it comes in close contact with the sample. It can thereby measure the analyte concentration of the sample, and the signal of the light can be then picked up by a photodetector and transferred into an electrical signal. There are some challenges when we're working with photonic chips. So photonic interfacing is one of the challenges. As you can see there on the top picture, we have glued the photonic chip with the fibers, so there's a fixed interfacing. But if you want to use consumable chips and you want to have a reproducible positioning of the chip, we have such a loose system like here, which is quite challenging. Challenging because we have to constrain the 6 degrees of freedom. The fiber can move with respect of the photonic chip. At the research group, we have implemented a theoretical model and confirmed it with measurement data. We can now predict the amount of accuracy that is needed in order for the alignment of the fiber with the chip. And you can see from this figure here that optical alignment in the center is rapidly decreasing to a lower signal as soon as you move away with the fiber for only a few microns. We're now approaching the investigation in a two-steps way. So photonic interfacing solution is now governed by a first step where we want to constrain as many of the degrees of freedom as possible by a fixation technique that is reproducible, such as the holder on top. We can also use a packaging design that folds nicely into a holder, so that pre-positioning is very easy. And the second step is an automatic alignment routine that as soon as the fiber is close to the waveguide on top of the photonic chip, you need actuators to move the fiber only for a few microns to search for the optimal incoupling of the light. So these are the steps we're making, and we're aiming for an easy and user-friendly, reproducible method for placing photonic sensors inside the device. I want to thank our students that have been working on this, and they participated in many educational programs, like some of the examples listed over there.
Okay, thank you, Sarah Maret-Rijn. Thank you for your presentation. Now, it's nanotechnology. It's not a field that I'm too familiar with. I know a little bit or so, but I'm not an expert as you, obviously. So I'm trying to understand this correctly. So you have these nanotechnology that is used in machines that doctors can use to measure a certain type of
analyte in a blood sample.
Yeah,
like
you can find out it's antibody for a certain disease. Yeah. And to be able to do that, you need to take away the sensor after you have done this to a patient. Because for a new patient, you need a new sensor, right?
Ideally, you want a clean sample or clean sensor for every new sample. Because every sample that comes in contact with the sensor, you have the risk of contaminating your sensor with previous samples.
Yes. But to be able for a doctor to place this sensor correctly, you need a device to do that. Because it's so specific, only a few nanometers difference will make the measurement worthless, right?
You're right. The alignment is very critical, so we're looking at feature sizes in the range of microns or submicrons. You can think of the optical fiber, as I've shown there. The diameter is many times smaller as a single strand of a human hair.
Oh, it's much smaller than the fiber that you showed is very tiny.
And the photonic chip has also feature sizes in that range. Okay. So aligning the fiber with the photonic chip is very submicron positioning.
Okay, but how do you even see? You cannot see the fiber. So how does it work? How does the device look like then?
So ideally, what we want to achieve is that the doctor holds a sample. Or not the sample, sorry, the sensor administers the sample of the patient on the device, but he doesn't want to hold the sensor itself because it's too tiny. So he wants a device like this, and then it can be put into the machine. So by doing so, he automatically aligns, he does the pre-positioning already by inserting the device into the machine. And then by pushing on a button, their fibers are automatically aligned as well with respect to the sensor. And then the analysis can start.
Yeah, and so in your research, how far are you with this? Does it work like you expected it?
Yeah, so we have some students over there that are presenting their work for the 3S Festival at the moment. The images I've shown to you are from them. They have designed a chip holder for the pre-positioning of the chip with respect to the fiber.
Yeah, a little bit looks like the way you insert your SIM card in your phone, right?
That's another research a master student of ours is working on. He's looking into the packaging of this really small and delicate sensor chip using this type of plastics for 3D printing, which is actually one of the first steps into looking into packaging of the photonic chips in the way that we are approaching it. So it's for holding the tiny, delicate sensor and administering it into a machine without contaminating of the sample.
Okay, so that's for the second part. But my question is again, does it work the way you expected it to, or?
We're working on investigating if it will work, but we have a good feeling based on the model that we made. we have some preliminary assumptions on how it should work. So the packaging will not resolve the prepositioning completely, but the automatic alignment can do that.
Okay, and so imagine this will work in the end. So you find something that will. How revolutionary would that be? What would it change in healthcare?
It would help point-of-care devices to become easier applicable in the world of photonics, so for consumable chips to be used in such devices.
Okay, and what kind of diseases can we use this for at the moment?
I think almost, well, everything is a large word, but
that's
the photonic sensor itself is very sensitive, and the selectivity of the photonic sensor can be chosen by the way we functionalize it, so the way we use materials to have the antibodies bind to.
Okay, so what you say is actually this one device can be configured to detect a lot of different diseases, not only one.
Yes, so if you have the photonic chip and you functionalize it with different materials, so it's accepting different antibodies, for example, from blood, then you can simultaneously run different diagnoses on the same platform.
Okay, so but what does that mean in real life? What does it mean to healthcare?
It speeds up diagnosing and testing, and it shortens the wait time a patient has to wait for the test results to come back from the lab. It usually takes up to a week before your blood is being analyzed and you can have the results spoken by with your doctor. And now you can do it on the spot.
How far away is this from being implemented in practice?
For me, that's difficult to say because I think it involves many parties, so especially companies, but also a lot of regulations in healthcare. So this is purely the technological side of it, but there's a whole world around it that needs to evolve accordingly.
Yeah, but I can imagine that sometimes you dream, so you're working on this research, on this very tiny scale research, but it can have enormous implications if it will all work, right? And if these types of devices...
It can, but I think hospitals and doctors' practices, the way that people work there right now is already quite an establishment, but protocols need to be changed for this sort of technology to enter that market. So imagine your doctor not having the time to wait for the blood results to come back and to think about your illness while he's taking a shower, for example. Well, with this technology, he has to find the diagnosis on the spot. I think that also in itself needs investigation because that can be facing some challenges as well.
Exactly. Okay, yeah, so the reaction time for doctors will also be much shorter.
Yes.
So we need maybe robots to take that work for him as well.
I don't know if we want to put doctors in that position, so that's something we should...
Yeah. Okay, thank you for now. We'll talk later, but first I want to introduce the second researcher. He is working at the Roesing Revalidatiecenter and at Saxion as a researcher, and he specializes in walking. And he will present research into an exoskeleton. Please welcome Chris Baten.
Thank you, everybody. This is weird, but we'll wait until we switch the laptops. Okay, my name is Chris Baten. I'm working at Roesing Research and Development in Enschede, but I also work 1 day in a week in the Ambient Intelligence Lectorate in Saxion University in Enschede. We're doing this to combine research on university type of research, which goes very much in depth, with practical solutions. And in projects like this comes very nicely together. The project is about a soft exoskeleton. You know, all exoskeletons are like Iron Man has it, which is a metal construction around the body, so you can be stronger and faster and whatever. But for patients, that's not really a good solution, although for some heavy cases, these things are made. But for all of us who get older and at some point get mild problems in walking, we look for more wearable solutions, so soft exoskeletons. This one? This one is forward, right? Okay.
Yeah, this is
Did you... Okay. At the beginning of the project, this was the way the exoskeleton plan looked like. And 6 years later, or actually 4 years later, it looked like this. So at least the graphics have improved, but let me tell you what we did also. This was a European project, so it's the work of a lot of groups and a lot of companies. You see them here, and what you actually, it's quite interesting, there's 2 applied universities, one in Switzerland and Saxion. The groups within Saxion that are working in this are the electorates of ambient intelligence, of smart functional materials and lightweight construction. But also from my institute, Routine Research Development, the wearable sensing group and the clinical gait analysis group. Okay, now it's working, I have to push the right button. Okay. Here you see the last drawings, and in this exoskeleton there are several components. There's a garment, so the textile. There has been work on the soft actuators and the soft sensors, which sense how the person is moving and which help the person move. There is let me see. Sorry, these are the soft sensors. Before it was the soft actuators. And then we have an evaluation system. We put 3D motion sensors on top of the whole thing to see if it actually was doing what we were hoping it would do. Okay. In a practical situation, it looks like this. You see a garment, and there is one of the actuators. And I cannot go in all the detail how it works, but it basically, at the proper point in time, gives a small pull in the leg to help somebody to walk better. You'll see later in a practical advantage how this works. And maybe I can explain later. As you can see here to the left, this is the final prototype. And if you look carefully, you see the guy is wearing a big backpack. This is not the way we envisioned it. It's supposed to be a trousers which you can actually wear underneath your trousers, etc. So this is far away from any practical solution. To the right, there's a movie with somebody walking with it, and you actually can see that the researcher walking with the person actually is wearing the backpack because it was too heavy for the patient. Okay, now I make a big switch because all these things in terms of the hardware, the sensors, etc. was done with other partners, but what we are most proud of is the part we did in the remote monitoring. So sensing what was happening and seeing, and that's what I will show to you. So basically what we made was some software which could communicate from the outside world with the exoskeleton, because we wanted to see in a different place what was happening. There is an authentication layer. If somebody was measuring, the data would be stored in a database. And that would be it. If there would be some calculations required, then automatically calculations would be started. They would put data out and in the database, and then everything would dissolve again. Then if somebody wants to see data, which could be a clinician with a laptop or a doctor behind his desktop at home, they can just request data and they get the data. And if the data is not there in the database, it could actually also be automatically calculated with the same structure. So this is the whole thing we put in place. I'll just resolve it quickly. And we had to do lots of stuff for that. For example, the software controls the whole exoskeleton. This is just an image from the screen where we can control all the elements in the exoskeleton, all the valves, etc., because it was a pneumatic system. We could switch it on and off, we can change the strategy. We could actually have options for calibrating part of the exoskeleton. And we could actually monitor all the sensors live, so the movement sensors of the extra system, but also all the internal soft sensors in the exoskeleton. We have 2 situations, use cases in which we want to use them. One is when people are moving freely around, for example at home, and we are at the clinic. And the other thing is when the patient comes to us in the clinic for training, fitting, testing. If you're in a free situation like at home and you get all the data in, but you don't know what the person was doing, you're lost. You cannot do anything with the data. So we also put lots of research in automatically recognizing activities at home. This picture is just to remind me to tell you this, but I cannot go into this very deeply. But you see here an example of 3 activities which a person is doing, which look different in the data, and the software has learned automatically how to recognize them and is actually able to recognize them. So it helps us to analyze all the other detailed data. Okay, when we're in the lab, then the whole thing is about accuracy. We use these motion sensors you see down there. We put them in all the spots where the orange arrows are, and then we can actually follow in 3D in very high detail what the person is doing. We made very complicated software, but all of this was actually meant to make things as automated as possible. So the clinical user was supposed to only, log in, say which patient it was about, set up the system with one push of the button, and then just start recording, stop recording, check the results, start again, stop again, and that's it. For this technology to be in such a practical form, that was actually a challenge, and it's very useful. In the lab, where we do the training, etc., we need the data to be extremely accurate, because an exoskeleton like this will only help a little bit. It will not make big movements. So we need also to have very precise measurement capabilities to do it. One example of an outcome of data. This is another one. This is a typical gait analysis set of graphs, where at the top you have the angles at the hip, in the middle the angles at the knee, and below the angles at the ankle. And the colors indicate the session. The green one is what a normal person is supposed to show. The orange one was when the patient came in for us the first time. The blue one is when the patient came in and we put the thing on, the exoskeleton, and we activated it. And we also have a black ones where the exoskeleton was on the subject but was not activated, as you can see here. For me, this was one of the more important graphs, because actually it showed nothing about the exoskeleton, because all the graphs are more or less on top of each other. But for us, it indicated that we were capable of very reproducible and accurate measurements. And it's actually more important, because this exoskeleton will be here, we'll test it, but the capability of being able to do these measurements, this precision, we can use it in many, many, many different applications. Okay, in patients, you see here a patient with and without the exoskeleton. At the right, the exoskeleton is activated. You see that at least the speed has also increased already, and this is a person who is not able normally to lift his leg in a normal way. You have to do this. Sorry, I'm in front of it. What you see here, for example, for this patient, there was some more hip flexion, the person has some more upright position, and you can actually see that the step length has increased here, which is an indication that it is very well helping the patient, although it seems a very little thing. Same thing here, sorry. This patient also had a longer step length, but that doesn't show up. And also the feet came higher from the ground without the person having to do all this, and that was very important. Okay, I'll go some conclusions. This is very boring, because it's kind of all the things we said in the beginning we wouldn't make, we made. But more important to us is that to make this whole system in a way which is very modular and flexible helped us a lot, because during the project the exoskeleton changed all the time and we could adapt to it. The other thing is the high automation in the software helped us also a lot, because normally these analyses take so long that you cannot have the data at the same point of time. You have to wait days before you get the analysis back, and that's not helping if you're developing stuff. And the last thing is, that in the home we'll have some issues with the observability. We cannot do all the measurements, but still what's left we are quite happy with. I think I should leave it at this. So thank you very much.
Thank you, Chris Baten. Please sit at the table. I was wondering, you presented the soft exoskeleton project, right? So yes. You also have these hard exoskeletons that are metal. Does the software, does it make any difference to the software parts that you worked on?
Yes, a lot actually. Because if you have a hard metal structure, you can put the sensors in the metal structure. And because the metal structure is very stiff, you can very easily measure angles, etc., just from the fact that you know that the metal will not bend.
And you know the length of the metal, you know...
Exactly.
Yeah.
Yeah, and in this case, when it's soft, everything is moving, so you cannot do the same trick again.
It's like the trousers, more or less.
In the first case, it's like you're measuring in a robot, and now you're measuring in this soft exoskeleton. Actually, it's like you're measuring an actual human wearing nothing. So we had to go to completely other different technology of measurement, which are these wearable motion sensors.
Yes, exactly. And you measure real time, right? So is that also the way the exoskeleton works? I mean, the calculations of how it needs to support someone, are these calculations made in the trousers itself, or
yes.
are they made at a distance?
No, they made the two things. First of all, they are based on the same sensors. On the movement sensors, also the sensors under the foot and the soft sensors in the fabric. But no, the calculations were all done on the subjects, because if the calculations are done away, then there is always the risk of a time delay, and that's very dangerous for control systems.
Okay, so there's
like multiple layers, a direct control layer and a more remote layer for analysis of.
So the system that you worked on, the monitoring system, was really to do that, monitoring and seeing what movements happen.
But part of the data was also fed back again to the exoskeleton, but they were not for direct control, but for slow changes in the control strategy.
Yes.
So on a different time constant.
For you, the same question as I asked before to Sarah. How innovative is this?
Yes, very innovative in a way that there's a few groups in the world working on this, and they're all at the same point like us, that it looks very promising, but it's not suited yet for daily use.
And what is the biggest obstacle to put it in place? Because you see that people move better, you just showed us.
Yes.
So what is the biggest obstacle to bring this into practice?
One little remark. Actually, it was quite rewarding for us to see that when we had to move from one room or the other, the patients were actually asking us to put it on.
Oh.
To activate it, so that was nice. But what is the most limiting factor? The version we have here, we had to switch technologies because the plan was way too ambitious. Halfway the project we switched technology, and the current technology is pneumatic. If you have pneumatic, so air pressure, you need some device creating the air pressure. So many of the experiments were done with a big device in the back of the room and a little tube to the person.
So you're always attached to a tube, so you can walk around in your house, but you have this tube.
To prove the point that it was portable, which I don't think is really useful, but it was done by giving a dive cylinder, small one, to the person, and there actually is a patient who walked around with it. But then the diving cylinder in itself was 3.5 kilos, the backpack already was 3.5 kilos. That doesn't make any sense.
Okay, so that is so if to be able to use it in practice, you need another technique than pneumatic.
For the activation.
Yes.
But there are actually some techniques coming up. We also see each other in conferences and stuff. I see already some promising other technologies.
Okay, and can you tell us something about who is going to use these types of exoskeletons?
Well, the ambition is that it would be because it's a light structure, it's fabric, you cannot have big forces. So it's for small problems. But any of us who gets older get at some point a problem with moving around. And the ambition and the intention is for these type of people, so basically for all of us when we get older, that at some point in time this could be, the extra trousers you put on underneath the other one.
Yeah.
Like many people take the electrical bicycle right now.
Okay. Did you put on the trousers yourself?
Yes.
And what happens if you're healthy and you walk fine? What happens if you put them on?
Yeah, they were not hindering me, but also not helping, because the protocols in there are very specific to this problem of the patient.
Okay, so it doesn't help you if you want to have a long distance walk to put on the trousers like that. And yeah, okay. Hey, a question for the two of you, because it's both health innovations, and there's one typical problem in health innovations always, and that is the costs and affordability of them. So are these types of innovations only for the happy few that can pay it, or will they be affordable to every one of us? Is there anything to say about that?
It's dependent on the area you're applying your technology for. So, for example, some tests are better served at centralized laboratories to have the samples sent over there. But other tests, there can be a benefit of having this type of technology where you have specific multiple testing on a single chip for one specific patient. I'm not so familiar with the financial figures.
Okay, so you don't know how much it would cost to have a sensor like that and a machine like that. Is it an expensive technology, or is it?
It needs some I feel uncomfortable in giving an answer because I'm not familiar with the
okay, so you don't,
numbers
you know.
that
and the exoskeleton, is that a
yeah, I think they will be much more affordable than current prosthetic and orthotic devices, because like an intelligent knee currently is on the market for 50,000 to 75,000 euros one piece.
Yes.
And I think this would be way, way, way cheaper. And that's also the intention, otherwise it's a failed project. But if I may add, also the measurement system, which we are very proud of, that we have this capability to do it very precise right now. We can also use that to make that like the stethoscope for the physical therapist. And to reach that point in time, we need quality, we need reliability, we need extreme quick application, and we need very low prices. And the prices is actually the least problem right now.
Okay, so you say the technology you developed, the software part, you can use it in more situations.
Yes.
And, yeah.
But still, to make it into a practical clinical product, the demands are extremely high in reliability. And
okay.
But we're getting there. We are still ambitious.
Okay, understood. I'm looking at the people listening here. Do you have any questions? Yeah, there's a question here, and I need a. Yeah, and we need to. Do you have a microphone? Yeah. Oh. Yeah. Okay, sorry. Go ahead.
For the exoskeleton, I have a question. You use accelerometers at the moment only?
No.
No?
We use EMUs. EMUs are motion sensing units, and in there are 3 accelerometers, 3 gyroscopes, 3 magnetosensors, a barometer, and a temperature sensor. Okay. And very highly sophisticated data fusion software algorithms.
Okay. Okay. So they are already integrated small sensors with all readouts and all. Is there a type of sensor that you miss? Something that you would like to see, but it's not here, or something that will improve the accuracy that you have now?
I would say the EMUs as they are quite capable of doing any angle-related data, angles, angle of velocity, angle of acceleration, etc. Also displacement acceleration, but they're not very good for positioning. In many clinical situations you don't care, but that would be an interesting addition. And the second thing would be that the sensors rely on the fact that they can observe the gravity, so they know what is down, and they can observe north by the Earth magnetic field, so you know what is front and back. But especially the last thing is in many environments disturbed. So we're working very hard to get this dependence of this technology on that observability of the Earth magnetic field to get it down. So we can actually also start using it in factories to, for example, measure people's backload.
So you are speaking about absolute positioning.
Sorry.
You said that the position itself of the sensor is a problem, then. Not the acceleration, the angular rates, and the. But angles. You want to have them, the relative position of the sensors. That's the challenge.
Yes, relative positioning, and in many situations you can get away with tricks, but there are also some situations we're still not happy.
Okay, and you have a solution for that?
We have to think about it.
Okay, he's thinking about it. So you talk later.
We'll have a coffee.
Okay, I have a final question because we need to finish off, and that is okay. Where do you move from here? What is the next step in your research?
Integrating the two-step approach, so integrating pre-positioning together with the automatic alignment and making it fast enough to be applicable and accurate enough and reproducible enough.
And you're working on that right now?
We're looking for funding to continue the research.
Okay, good. And what about your research? How long is the program
to make it more
running?
reliable, cheaper, practical, but also to add big data science, because when we are capable to measure people more, then we will drown in the data. And especially the group I'm in right now, they have a lot of knowledge on dealing with that. So.
Okay, good luck with the rest of your research, and thank you for here. Give them a warm applause. Chris Baten en Sarah Maretrijn.
Thank you.